Now, everything we've looked at with motion, all the functions are in terms of time. But there's no reason why it has to be. We can describe motion in terms of its position or its displacement as well. So that's what we're just going to have a look at now, velocity and acceleration in terms of displacement. So velocity is some function of displacement, some function of x. Now, in that case, we've got this wonderful formula for acceleration that we can use. d dx of a half v squared. Now, it's important we use this because we know that when we want to go from velocity to acceleration, okay, we differentiate. We've got that in our heads, but that's when it's respect to time. When it's with respect to displacement, that won't work. Okay, as I say, we know acceleration is the derivative of velocity with respect to time. I could use our implicit differentiation, chain rule, call it whatever you wish, but I could rewrite that as dv dx times dx to t. Now dx to t is of course velocity. So it's now dv dx times velocity. I'm going to rewrite velocity. Velocity would be the derivative of a half v squared with respect to v. In other words, differentiate half v squared with respect to v, you get v. But now the dv's, if you like, cancel, and I get that acceleration is the derivative of a half times velocity squared with respect to x. So if velocity is written in terms of x and we wish to find acceleration, we don't just differentiate it straight away. We have to actually differentiate a half v squared, not just v by itself. So let's have a look at an example. Acceleration this time has actually been given to us. It's in terms of displacement, 3 minus 2x. We want to find its actual velocity in terms of displacement. So in this case, we want to go back the other way. All right, but I know acceleration is the derivative of a half v squared with respect to x. So therefore, if I want to undo the differentiation, I've got to do the opposite, just like any equation. I'll integrate both sides. So I get a half v squared is the integral of 3 minus 2x. So I get 3x minus x squared plus, of course, some constant. We've been given some conditions. Velocity is 2 when displacement is 1. So we can sub in and work out our constant. And so there's an expression for velocity squared. Now, they haven't asked for an expression for velocity squared. They've actually asked one for velocity. So I need to keep going. Velocity, therefore, is plus or minus the square root. You see, it is possible to have two velocities. When it was with respect to time, it wasn't. Because at any time, you could only have one velocity. But it's not with respect to time, it's with respect to position. So it is possible to have two different velocities at the same position. They'd be at different times, but it's at the same point. So you might have travelled out somewhere and came back. But if you did that, then each position you'd be there at two different times. One when you were going out, one when you were coming back. So it is possible for velocity to be both plus or minus when we're talking about with respect to displacement. Okay, so things to note here. I know that velocity squared obviously is always going to be greater than or equal to 0. Or another way of thinking about that is whatever is under the square root sign has to be positive. So that's a way we can actually work out the path of the particle. Because I know 6x minus 2x squared must be greater than or equal to 0. I can solve that inequality and we get x is in between 0 and 3. So we know the displacement for this particle must always be between 0 and 3. It has a very boring life, just between 0 and 3. 2 it can visit, 1 it can visit. Pi, what's that? It never gets there. Okay. So this one moves between 0 and 3 and nowhere else. Okay. Here's one. Acceleration this time is 3x squared. Particle is 1 unit to the right of the origin. We're going to go all the way and actually find the equation for displacement in terms of time. So let's start like I did with the other one. They've told me acceleration is 3x squared, but it's in terms of displacement. So d dx of a half v squared is 3x squared. We'll integrate both sides. So half v squared, x cubed plus a constant. There must be somewhere in the question something that links displacement and velocity together. What do we got? Initially, it's 1 unit to the right, so x equals 1, travelling velocity of root 2 in the negative direction. So we know when at time equals 0, although I'm not going to use t in this one, of course, x equals 1, velocity is minus root 2. Nicely, conveniently works out to be 0 again for the constant. So my velocity is plus or minus root 2x cubed. Now we're trying to find the expression for x in terms of t. Well, velocity is, of course, dx to t. So now I can get a relationship between x and t. However, I no longer have both plus or minus, because if I'm now going to relate about at a particular time, it can only be one thing. I chose minus. Why did I choose minus? And the reason is I've got to match up the initial conditions. And so the initial condition said velocity was negative root 2 when x is 1. And so when I sub in x equals 1, I need to get an answer of negative root 2 because they're the conditions I'm using. So to go a step further, I'm going to use negative square root for this problem. Okay, I have dx to t, so to undo the derivative, I'll integrate both sides. I'll turn it into index form first to make life a bit easier for myself. And I'll also turn it upside down, because if I'm going to integrate, right-hand side is in terms of x. So I need to integrate with respect to x, so dx needs to be on the bottom there. So turn it upside down. I now have the t dx is minus 1 on root 2 x to the negative 3 on 2. So t will be, add 1 to the power over the power, tidying that up. I've got square root of 2 over x plus a constant. So now go back to the conditions we got. When t equals 0, x was 1, I think it was. Yes, it was. Sub that in. Constant this time is minus root 2. So I've almost answered the question. I now have time in terms of displacement. But the question said find displacement in terms of time. So I now have to rearrange this and make x the subject. So, another way I could have got to the t. I could have done it as a definite integral, which would have saved me not worrying about the constant. And I could say, well, time will be the integral, which is exactly what we did. But I'm starting when at 1 and going to x, some general position. Okay. And so then it becomes just a definite integral. Sub x in and minus sub 1 in, and we actually end up with the same result. It's another way of doing it, using definite integrals instead of indefinite integrals. Okay, so we'll move the root 2 to the other side, square both sides, turn it upside down, multiply by 2, and eventually I've got a formula there in terms of time. All right, so an HSC question. Particle moving along the x-axis as we love to do, position 2 meters to the right, and just in case we can't interpret that, they've helped us out there. That is x equals 2 when t equals 0. Initial velocity 5 meters per second. Acceleration is 2x cubed plus 2x. We've got to show velocity is x squared plus 1. So again, same sort of a question. It's in terms of displacement. d dx of a half v squared. Integrate both sides. Now we'll work out our constant. X equals 2, v equals 5. Constant in this case is a half. So v squared ends up being x to the power of 4 plus 2x squared plus 1. We have to show v, or velocity, is x squared plus 1. Well, nicely, that happens to be a perfect square. So in fact, v squared does equal x squared plus 1 squared. So v does equal x squared plus 1. But we should make a note why we chose the positive square root, not the negative square root. Otherwise, it sort of looks like we're just fudging and jumping straight. Oh, well, I know the answer's got to be x squared plus 1. So we need to explain why we chose the positive. So I've said, well, v has to be greater than 0 in order to satisfy my initial conditions. So they can see, yes, I did consider the possibility that it might have been negative. Hence, so really just the same sort of question again. Find an expression for x in terms of t. So dx to t is x squared plus 1. Turn it upside down. Again, I'm doing it as a definite integral. Probably a better way of doing it as a definite integral. You'll notice on the left-hand side, I've also done it as a definite integral as well. This is an unusual way of doing it. We don't normally see it this way. Normally, we just write t. But the reason why we write t is because we're integrating from 0. We're starting at a time when t equals 0 to some random time t. And when you integrate the constant, you'll get t, and t minus 0 is t. So normally we just end up writing t when we integrate. But that's really what we're doing. It's not a bad idea, especially if, say, your conditions isn't when t equals 0, because basically you match the limits. So down the bottom I say, well, t equals 0, displacement is 2. And at the top, I'm trying to find a general formula for when t is t and displacement is x. And so do both sides. So the left-hand side, as I say, becomes t. Right-hand side is an inverse tan function. And so we have inverse tan of x minus the inverse tan of 2. But that's t in terms of x. We want to find x in terms of t. So inverse tan x is t plus inverse tan 2. So x is the tan of t plus inverse tan 2. Probably good enough to get the answer, I would think. I mean, it is an expression for x in terms of t, but us super mathematicians. Tan plus tan on 1 minus tan tan. Right, because you're saying the tan of the inverse tan of 2 is going to be 2. So tan of t plus tan of the inverse tan of 2 over 1 plus... Doesn't that look much? But as I say, they probably would have accepted. I'm sure they would have taken just the tan of t. And so. All right. So let's add 3e to our list. We'll have a look at this idea of acceleration and velocity in terms of displacement.